Okay, welcome to Math372 Complex Analysis, Lecture 3. So what we're going to do today is we're going to do some consequences of sequences in series. And so we're going to start proving the different results in complex analysis about differentiable functions. One of the most important results is that if your function is differentiable, you have a series expansion that converges in a non-trivial neighborhood and equals the function. And we've already shown, or we've talked about, if you're differentiable once, you're differentiable infinitely many times. So a very different subject than real analysis. So in real analysis, you have the comparison test, the ratio test, the root test. There's a few other tests, but these are the big ones. The ratio and the root test are much easier to use than the comparison test. Why? There's an explicit formula. It's a do-read. It's a very specific, spelled-out procedure. It's like the quadratic formula. You just plug it in. You do the algebra. The algebra may be hard, but it's prescribed what you should do. The comparison test is almost more art. You have to figure out what's the right series to compare it to. If you find the right one, then it's easy. If you don't find the right one, it's much harder. Now, the proof of the ratio test and the root test actually boiled down to doing a nice comparison. And they do a comparison with the best sequence of all time. Well, at least a sequence with infinitely many terms. So what is our favorite infinite sequence? Geometric. Okay. So the geometric series. So 1 plus x squared equals the sum, n goes from 0 to infinity, of x to the n is 1 over 1 minus x. At least if the absolute value of x is less than 1. There's a lot of ways to prove this. I'll sketch some in the additional comments. In my probability class, we do this with a memoryless process playing a basketball game. What you can also do is you can look at the finite series. Sn is 1 plus x to the n. Look at x times that, which would then be x plus xn plus xn plus 1. And then if you subtract, you get 1 minus x times Sn is 1 minus x to the n plus 1. So you get Sn is 1 over 1 minus x to the n plus 1 over 1 minus x. So I like this formulation of what the geometric series is because, I should have checked where the erasers were before the class started, because you can see here's what it's converging to in the limit. Here is the difference at a finite level. You can see if the absolute value of x is less than 1, this term is going to be going to 0. You have a sense of how quickly it's converging to the limit. Now, some of the results we're going to want to do is if we have a series that converges, let's say it converges absolutely, we'd love to be able to differentiate term by term and have that be the derivative. The problem is we then have to interchange a sum and a derivative. Is there anybody here who's also a physics major? Okay, good. So we don't have to worry about anybody not caring about justifying interchanges. Right? This is the heart of mathematics, is can you switch the order of two operations? Often the answer is yes, but not always. I will link to a video of Cam when he was about 2, where he learned how to switch the order of summation by waving his bubble wand. It has to be justified. Now, how would you justify interchanging a sum and derivative? Well, we can go through a rigorous real analysis proof, which is what we will do. For the geometric series, however, we have an interesting way to justify the interchange. And I want to just mention this because if you can prove a special case easily and get some information, let's do that. So here's the infinite sum. What I can do is I can write this as Sn of x plus the sum, n goes from n plus 1 to infinity, of x to the n. This will just be the sum of the first big N terms. What can you tell me about this over here? What is this quantity here?
Small.
It's small, but it's more than just small. What does this look like? It's a geometric series. So we can write this as Sn of x. Now we'll pull out the first term, which is x to the n plus 1, and then we'll have a sum, n goes from 0 to infinity, of x to the n. And since we know the geometric series formula, we'll now get x to the n plus 1 over 1 minus x. Now if we want to try to justify differentiation term by term, I can take the derivative of a sum. Derivative of a sum is the sum of the derivatives. You can take the derivative of finite sum as the finite sum of the derivatives by just grouping things with parentheses. So if I have, f plus g plus h prime, this is f plus g plus h prime, which is f plus g prime plus h prime, which is f prime plus g prime plus h prime, which is f prime plus g prime plus h prime. Massive overkill. That's what you need to do to justify going from the derivative of a sum is the sum of the derivatives to the derivative of a finite sum is the finite sum of the derivatives. But it's important that it's a finite sum. For an infinite sum, we need to do work. So here, because we notice that the tail of a geometric series is itself a geometric series, I now just have two terms. I can take the derivative of this term, which is now just going to be nx to the n minus 1. And now I want to take the derivative of this term. So I get like an n plus 1 coming down. And when you do all the algebra, which I encourage you to do, you can see that the derivative of this piece will be going to 0. And then when you take the limit, it does seem that it should be the derivative of the infinite series is the sum of the terms. So again, whenever you can build up intuition, it's worth doing that. OK, so what do we need now? We need the concept of a radius of convergence. So we will have a series, the sum, and it goes from 0 to infinity of an x to the n. And we'll let r equal the limit as n goes to infinity of 1 over the absolute value of an to the 1 over n. I'm just making sure I am doing things correctly. All right. I'll do it the other way. So the book has it as 1 over r, so I'll do it as 1 over r. It makes no difference. So lim sup of an to the 1 over n. So r is the radius of convergence. So if the absolute value of x is less than r, it converges. If the absolute value of x is greater than r, it diverges. If the absolute value of equals r, who knows? We want to be in places where things converge absolutely. So not only is this converging, it's converging absolutely. That means we can put in absolute value signs. Whenever you can put in absolute value signs and things still work, you're in great shape. If you remember the Fubini theorem, how many of you have seen proof of Fubini interchanging orders of operation of integration? OK. So we will talk a little bit about that, or I'll put some notes about that. You cannot always switch the order of integration. One of the key conditions is if the double integral of the absolute value is finite, then you can switch the order of integration. And so it's the absolute convergence that is really driving a lot of what happens. If you think about what's going on here, let's say the lim sup of an to the 1 over n is equal to 1 over r. If I take x to be a little bit smaller than r, then this quantity over here is going to be bounded by something like a little bit less than 1 to the nth power. And then you can win by the comparison test. So that's what's really looking in the background. Really, it's another application of a comparison to the geometric series. No. When in doubt, the geometric series is our go-to series for understanding anything. We understand what the geometric series is like. That's what's looking here. So what we want to do now is we want to justify differentiating term by term. We want to switch the order of summation and differentiation. It is not always possible. When I was a postdoc, I was working on a project for a couple of months. It came down to I needed to switch an order of integration, and I eventually proved that to do so, we needed a parabola which was pointing up and had leading term negative, at which point the entire research project collapsed because there is no such parabola, and the interchange was not justified. So, big theorem. If f of z equals the sum of an z to the n n equals 0 to infinity converges absolutely for z less than r, then f prime of z is the sum, n goes from 0 to infinity, of n an z to the n minus 1. Basically, you can just do term-by-term differentiation. So the first thing to note is I've given you a series. Whenever you see a series, what's the first question you should ask about the series? Does it converge? So, proof. So first, the sum, n goes from 0 to infinity, of n an z to the n minus 1, let's call that g of z, converges. I should not call it f prime right now because I don't know it's the derivative. I'd be shocked if it wasn't, but I don't know that it's the derivative. So we need to calculate the radius of convergence. So let's calculate the lim sup of n an to the 1 over n as n goes to infinity. So this will be, the lim sup as n goes to infinity of n to the 1 over n times an to the 1 over n. We know what the lim sup of an to the 1 over n is. What's n to the 1 over n going to? It's going to 1. So how would we prove n to the 1 over n goes to 1? Yes, now we can finally do logs legitimately. This is a Miller class. If you go an entire week without taking a log in a class taught by me, something is wrong. So note that the log of n to the 1 over n is the log of n over n. And then if you L'Hopital it, so again, great mathematicians become verbs. So when you L'Hopital log of n over n, what's the derivative of log of n? That's 1 over n. The derivative of n is just 1. That's 0. So if the log of this quantity is going to 0, that means n to the 1 over n is tending to 1. So you can get this as close to 1 as you want. So the lim sup of this quantity is going to be the same. So the series will converge in the same region. Okay, this is a good start. They at least have the same radius of convergence. Now we want to show that they are equal to each other. So the way we do this is one of the standard results in real analysis. How many of you have seen a 3 epsilon proof? You break something up into 3 quantities. You show each quantity is less than epsilon. Therefore, the whole thing is less than 3 epsilon. If you are really good, rather than showing each quantity is less than epsilon, what do you do? Epsilon over 3. If you really want to show off to people, you're adjusting so that at the end of the day, you have a nice thing less than epsilon. After a while, you realize it doesn't matter. If your final thing is less than 3 epsilon, it's okay. You can then just do a search and replace with all epsilons, with epsilons over 3. This is the 21st century. I was at a dinner last night and somebody was talking about how remarkable it is to just be able to do Control F. Okay. I actually think Control R is somewhat better sometimes than Control F. So this will be a 3 epsilon proof. And what we're going to do is we're going to use the geometric series to motivate us. So what do we do for the geometric series? We chopped it off very far down and said, here's the good part, and then here's the bad part. But the bad part is really small, and it shouldn't make too much of a difference. The problem is your quantity could be small, but it could be highly fluctuating and have a large derivative. So for instance, I could give you something like this. And then the quantity itself is small, but the fluctuation is enormous. If I've done this right, it's not even visible on the computer. Okay? So we need to show that the derivative is small, that the tail is not really mattering. So what we're going to do is we're going to start off with f of z as the sum n goes from 0 to n of an z to the n plus the sum n goes from n plus 1 to infinity of an z to the n. And we're going to call this Sn of z plus En of z. And the idea why E? Error. Right? You always want notation that reminds you of what's going on so that you can glance down and see what's going on. This is the error in replacing f with Sn. And the hope is that as n gets very, very large, not only is the error, but the derivative of the error is small. Is Sn of z hard to take the derivative of? No, it's a finite sum. So now we can go through and try to understand the derivative. So f prime of z, oh, can I write f prime of z at this point? I mean, if I want to write this as, the limit as h goes to 0 of f of z plus h minus f of z over h. I can write it like this. I don't know yet that this limit exists. So if you want to be extremely pedantic, you can yell at me. I should not be writing f prime of z until I know the limit exists. So this is going to be the limit as h goes to 0 of Sn of z plus h minus Sn of z plus En of z plus h minus En of z over h. Okay? So I've just split things up because I know where the proof is going. Let's put the two Sn's together. Let's put the two E's together. So a lot of you have taken a class with me before. I'm going to put you on the hot seat now. I love taking logarithms. But there's something else I love to do. What else do I love to do? Yes, I love to do nothing. Right? And what are the two ways to do nothing? I can add by 0 or I can multiply by 1. And as one of my professors, Peter Jones at Yale, told me, the log of 1 is 0. So there's really only one way to do nothing. So when I have something like this, and I want to analyze this, this is the whole point of the class. I want to really drive home how you come up with these proofs. We're starting with the definition of the derivative. We're building on our example of the geometric series where we understand what's going on. I know what the derivative of Sn is. That's not hard to work with. And I also have a candidate, right? What's the candidate?
It's the G over there.
So it's the G over there. So we think that at the end of the day, we should be able to, have that G coming into play. So the question is, do we want to study this, or do we want to study this maybe minus G of z? And show that that's tending to 0. So this is the definition of the derivative. Since we think it should be going to G of z, let's subtract off G of z. And now this quantity over here looks like the finite approximation of this. So maybe what we should then do is put in the finite approximation of that. And so what we're going to do is we're going to add 0. So we'll add Sn prime of z minus Sn prime of z, which equals 0. But the point is, I want to give you a sense of why we're electing to do the algebra in this way. Bless you. Okay. So proof continued. So we will have the limit as h goes to 0 of Sn of z plus h minus Sn of z over h minus Sn prime of z plus the limit as h goes to 0 of Sn prime of z minus g of z plus the limit as h goes to 0 of En of z plus h minus En of z over h. And since everybody else gets a bracket, I'll give that one a bracket. Okay? So we've added and subtracted Sn prime of z. And so the way a 3 epsilon proof works is you reduce it to 3 different quantities, and you show each quantity is small. So you've got 3 choices. Which one do you want to look at first? Which do you think is the easiest? The first one. Why is the first one the easiest? It's the definition of the derivative, right? So the first one is small by the definition of the derivative. We have a finite sum. So we've got to be very careful about the order in which we do things. Are we choosing an n and then choosing an h? So given any n sufficiently large, there is an h such that the first term is sufficiently small. So for 1, given an n, there exists an h which is a function of n such that first piece is less than or equal to epsilon. And then if we have multiple n's, we just choose the largest n so that all of them will work. And if we have multiple h's, we just make sure they're all smaller than the critical threshold. So such that the first piece is less than epsilon for all h sufficiently small. So if you want, what you would technically say is there is an n1 and there's an h0 depending on n1, such that the first piece is less than epsilon for all h less than h0 when n is greater than n0. Or maybe, I'm sorry, we're doing 1. We should be doing 1s here, because we're looking at the first piece. OK, so that handles the first piece. Now we've got the second and the third piece. Which piece do you think is the easiest one to handle next? The third. Why the third?
Because it's a geometric series.
The third is not a geometric series because you have a z plus h.
Oh, yeah.
Then the second. So sometimes things are actually written in an order of increasing difficulty. This happens to be one of those times. The second one is, I think, the next easiest one to handle. And the reason is, if you look at what's going on, Sn prime is just the beginning of G. So second piece, what do we have? Sn prime of z minus G of z is just going to be the sum, n goes from n plus 1 to infinity, of n, an, zn minus 1. But we know this series has the same radius of convergence as the original series. This is the tail. Because the series converges, the tail can be made arbitrarily small so long as you are sufficiently far. So we just have to choose big N sufficiently large so that this is small. So choose N so large, I guess N2 so large, that for all n greater than n2, it's at most epsilon. Yes?
Why is it that we can use n to make it smaller if the limit is as h goes to 0?
I'm sorry?
Why is it that we can use n to make that small if we're evaluating the limit as h goes to 0?
Right, but at the end of the day, we're trying to show that this quantity is less than epsilon for any epsilon.
Oh.
Right? So all I need to do is I need to make this quantity small. So this is a good question. There is no h here. So if the only way we can win is to work with h, we're in trouble.
Yeah.
So fortunately, we have 2 things at our disposal. And this makes it a little bit complicated in terms of the bookkeeping. Which are we working with? Are we working with n or are we working with h? But think of this as the easiest possible limit on h because there's no h dependence.
Yeah.
So then we just choose n so large that it's small. OK. Only one term left, right? We now have to roll up our sleeves and handle the third term. It is not sufficient to do 2 out of 3. Right? This is not a Meatloaf song. Anybody get the reference? Not one person. OK. So let's look at the third piece. Am I in focus? OK. So now piece 3. And this is the harder one. So we have En of z plus h minus En of z over h. What makes this piece potentially hard to analyze? What's problematic?
We have the z plus h.
So we have the z plus h, which is going to be expanding things outward. That's one problem. What's the other problem?
It's also not a finite sum.
It's also not a finite sum. What else? We got a lot of issues with this piece. There's one more issue. We didn't have this in part 2.
Oh, there's an H.
There's an h, right? There's an h in the denominator. So as h goes to 0, the denominator is going to 0, and we're dividing by a number getting smaller and smaller and smaller. So this piece is far harder to analyze. Well, let's see what's going on. This is going to be a sum, n goes from n plus 1 to infinity, of an z plus h to the n minus z to the n over h. The first thing we have to be careful about is, are we even legally allowed to look at this? So why might we not be allowed to look at this? It's so easy to assume things, yes. Any idea why we might not be able to look at this?
Well, if it doesn't converge, then we can't put them together.
Okay, so why might something not converge?
Because the H took it out of the radius of convergence.
So the h could have taken it out of the radius of convergence. Oh, that would be annoying, right? So imagine we have our point z0, we have our radius r, and we have our point z. Well, all we have to do is make sure that we choose h so small that we're still inside the radius of convergence. We can do this because it's an open set. It's nice at some point to use some of the assumptions of the problem. So we have open sets. This is why we like open sets for differentiation. Everything is a local phenomenon. We just make sure we stay away from the boundary. And now we can actually talk about this. But it's very easy to write things down and be outside the radius of convergence. Okay, so at least the series makes sense. So we want to study what is z plus h to the n minus z to the n. We could expand this out with the binomial theorem. Does anybody recognize z plus h to the n minus z to the n?
Oh, there's an identity for this.
Yes.
Well, it's like if you have a to the n minus
Good,
b to the
good.
n.
So let's just look at it as a to the n minus b to the n. What can you pull out?
A minus b.
You have to be able to pull out a minus b, because if a equals b, it's 0. So this has to be a multiple of a minus b. And then a little bit of work, you get a to the n minus 1 plus a to the n minus 2b. Was it not 2b? No, it's 2b. Plus b to the n minus 1. And so now if we take absolute values, the absolute value of an minus bn is equal to the absolute value of a minus b. Actually, let's do less than or equal to. And then it's going to be less than or equal to the maximum of absolute value of a, absolute value of b to the nth. We could do it to the n minus first power.
What do you have to multiply by?
And then we have to multiply by, how many terms are there?
There are n.
There are n terms. So when we look at that, this quantity here can't be too large. Because z plus h minus z, we're going to have an h over here, which will cancel with the h down below. And so then the rest of the stuff, well, we'll have either z or z plus h, but both of them will be less than the radius of convergence. And so now our quantity, I guess I'll come back over here. So when we look at, we'll let A be z plus h, and we'll let B be z. And so now, when we look at a to the n minus b to the n, this is going to be an absolute value less than or equal to h times n times r minus say epsilon prime to the n minus 1, where r is the radius of convergence. Will be a little bit less than that. And this epsilon prime will be independent of how small h is. As we make h smaller and smaller and smaller, this bound will still work. And so now we get the third piece in absolute value is going to be less than or equal to the limit as h goes to 0 of the sum n equals n plus 1 to infinity of n, a, and we have to put in an absolute value here because we're taking absolute values, r minus epsilon prime to the n minus 1. And this series has the same radius of convergence as the others, so same radius of convergence. Therefore, there exists an n3 such that for all n greater than n3, if h is sufficiently small, the third piece is less than epsilon. And now we just have to put them all together. So this proof takes a little bit longer than one would expect. I was looking at the clock to get a sense of roughly how long the thing's taking, because the location here is not great when I'm on that board. So this was about half an hour. We spent a little bit of time with the geometric series. But it's a lot of stuff here to go through very carefully and show that you can differentiate term by term. This is one of the reasons why in a lot of subjects, oh yeah, you can just go on. And they don't really spend the time justifying stuff like this. Whenever you prove a result, you always want to mine it as much as possible. We've just proven if you have an analytic function, so a function that's given by a Taylor series that converges, you can differentiate it term by term. What can you do now? What else do we know? And somebody made a comment about this on the first day of class.
You can integrate it or differentiate it instantly.
Good. So we can differentiate it again. Because now f prime of z is given by this Taylor series that converges. And we can differentiate this term by term. And its derivative is given by the term by term. So we actually get as a corollary, right over here. So corollary, f equals the sum of an z to the n. F is infinitely differentiable term by term. That's really nice. Did I use anything about complex analysis here?
Well, you must have, because it doesn't work in the real numbers.
Could be very careful.
Well, you have to assume it's analytic.
I have to assume. So if I have a function which is given by its Taylor series, then I know it's infinitely differentiable and the derivatives of that. That result also holds for real valued functions. If you have a real analytic function that is given by an infinite sum, then this result is true. If I just know that the function is once differentiable, I don't know right now that that means it's given by a Taylor series expansion. The main reason I have to check my notes before lecturing today, and I know there's at least one person in this class I was talking to about this yesterday, is I always forget at what point in the semester do we know certain facts. It is quite annoying. Because once you take complex analysis, you have all the theorems at your disposal. When you're teaching complex analysis, it's like rocket boosters. They kick in at certain times in the semester. Right now, we don't know that complex differentiable implies analytic, which then implies infinitely differentiable. But this result would hold for real analytic functions as well. All right. Because most of you have not seen the stuff on Fubini's theorem, I want to give an example now where you cannot interchange orders of operation to just really alert you to the dangers of the subject. After doing a 30-minute proof, I don't want you to think that this is always justifiable. And this is one of my favorite examples. Now, normally when you do examples in multivariable calculus, you work with continuous functions. I'm going to work with discrete sums. You can always smear things out and make them continuous. I don't really want to do that. So when Fubini fails, So imagine the infinite grid of non-negative integer pairs. In the interest of time, I will only draw a finite subset of it. So this is the point 0, 0. This is the point 1, 0, etc., etc., etc. And I'm going to find a sequence A and M as follows. It's going to be +1 here, -1 here, and 0 going off to infinity. Over here, it'll be 0, +1, -1, and then 0 going off to infinity. 0, bless you, 0, +1, -1, 0 going off to infinity, and so on and so on. So we want to study, it's like the battle of the giants. But now I have to be careful, and I want to write my sums. This will be n goes from 0 to infinity, and then m goes from 0 to infinity, whereas this one will be first m goes from 0 to infinity, and this will be n goes from 0 to infinity. So here I fix an m, so that means I fix a height, and I sum over that row. What can you tell me about all the row sums? Or maybe almost all the row sums. Almost all the row sums are 0, except for that first row sum, which is 1. So this quantity here is just +1. For this quantity, I fix a column, and I sum up the column. What does each column sum to? 0. As an exercise, prove that 0 does not equal 1. So this tells us that there are situations where you can't switch orders. If you want, what you could do is, of course, just draw like a small circle of radius 1/4, and then just spread the +1 and the -1 into that region, and then you can have an integral. What goes wrong is if you try to do the double sum of the absolute value, it blows up. And the real condition you need to justify the Fubini theorem is you want something that's absolutely integrable. Whenever you have infinities in mathematics, things are dangerous. It could be infinity because you're looking at an infinite space, because the values get arbitrarily large. Every time you see an infinity, you have to be careful. Okay? We have an infinite sum. We're working with a lot of infinite sums. We've got to be very careful that we are not doing anything illegal. Okay. Any questions up till now? Okay, so we've now finished the proof of a big theorem. We're going to isolate this as a nice definition. And so I've said this informally a few times. We will call functions that are given by a convergent series analytic. So we say f is analytic if f of z equals the sum, n goes from 0 to infinity, of an. I'll go z minus z naught to the n. For all z in, say, a ball of radius r about z naught. So this will be the set of all z such that z minus z naught is less than r. Let's take r to be greater than 0, so it's worth talking about. And then a function is analytic in a region if it's analytic at each point. But this is a local property. It's what's going on at a point. It's what's going on in a small neighborhood of that point. And so we already have a theorem that an analytic function is infinitely differentiable. Okay? So the question, of course, is which functions are analytic? So that's going to be one of the big motivating questions. Question: when is f analytic? So I gave you either one of the best or one of the worst functions in all of mathematics. The function f of x equals e to the negative 1 over x squared if x does not equal 0, and 0 if x equals 0. This is a nice function in some sense. If you use L'Hopital's rule, all the derivatives exist at the origin. The derivatives exist everywhere else. The problem is it's really flat near the origin. And when you look at the Taylor series has all coefficients 0. So the Taylor series of f is just identically 0. So the function is not given by its Taylor series in a small neighborhood about the origin. This should be troublesome. Now this is a class in complex analysis. What should I replace x with? Let's replace x with z and see what happens, right? You know, we should do at least some complex analysis today. Okay. All right, so we've replaced it with z. There's only one trouble point. It's still z equals 0. How do you want to figure out what's going on at z equals 0? Take different paths. Good. What's one path we should take? Imaginary. And what's the other path? The real path. So we've already done the real path. So on real path, the limit as h goes to 0 of f of h equals 0. If we take the imaginary path, let's say z equals ih with h real. So I really like writing something like this. If I know it's imaginary, write it as I times something real. Then we would have e to the minus 1 over z squared is e to the, now I squared is minus 1. So this is 1 over h squared. What does this go to as h goes to 0? It goes to infinity. As h gets really, really small, 1 over h squared gets really, really large. This goes to infinity as h goes to 0. So if we look at this function in the complex plane, it's going to 0 along the real axis, and it's going to plus infinity in absolute value. It's going to plus infinity along the imaginary axis. Is this function differentiable? No. In fact, it's not even continuous. So not complex continuous. If it's not complex continuous, we should not even be asking about, is it differentiable? And we shouldn't be asking about its Taylor series. You know, a prerequisite, an ante for the conversation, is the function must at least be defined at the point. It's not. So this tells you what's going on. When we look at the extended function, which the real valued one was just a small subset of, we see the issue. Okay, so I think we've got about 5-6 minutes left. Okay, so all I want to do now for the last bit of class is we've talked about what it is to be analytic. I want to just state the main result of what we're going to be doing for our integration. So integration on paths. Now, we will eventually leave Calc 3, but this is yet another instance where Calc 3 is helpful. How many of you remember path integrals? Where you have some kind of curve in space. So you have an interval AB, and you have some map, say gamma, which maps it to, you know, a curve in space. And the space could be the plane, it could be 3 space, it could be higher. And you'll have, you know, gamma of A is the start of the curve, gamma of B is the end of the curve. Maybe gamma is piecewise continuous. Maybe it's differentiable except at finally many points. Maybe it's closed, so gamma of A equals gamma of B. And so what we're going to do is, by the integral along some curve of gamma of, you know, f dz, we're going to mean like the integral from A to B of f of z of t, z prime of t dt. And so this is going to be a nice one-dimensional integral that we can look at. So we're going to want a way to parametrize a curve. So t will go from A to B, and z of t will trace out the curve. If I'm writing this integral, this is supposed to represent the integral over some curve gamma. Gamma is something physical in space. It should not matter how I parametrize the curve. Or maybe it should matter, but it should only matter weakly. If I have two parametrizations that have the same orientation, that they both start at the same point, they both end at the same point, and they're both one-to-one maps. I'm not tracing part of it back and forth multiple times. Well, if I go forward, back, and forward, that's the same net effect as just going forward, so that's okay. The main thing I have to be careful about is I don't want to go forward for one and backwards for the other, because then I would have a difference by 1. So the main result is that this integral should be independent of the parametrization. So the proof is given in the book. It's just a few lines. Any thoughts what the key ingredient in the proof is? It's a Calc 3 result that is sadly often forgot. Chain rule, change of variable. So chain rule, change of variable. It's independent of the path, at least if same orientation. And if you want, you can think, since f is, u plus iv, and z prime would be, you'd like u prime plus iv prime, or I guess they would be different ones. This would be, you would have two components for f, two components with z. It's very similar to a dot product. So let's look at some of the most important examples. Circle of radius r about z naught. So here is z naught. With a good imagination, that's a circle of radius r. And so I could write z of t is z naught plus r e to the 2 pi I t. T goes from 0 to 1. And when t equals 0, I would start off over here. And as t goes all the way around to 1, I increase by 2 pi. I come back over here. And that will be the clockwise. I'm sorry, counterclockwise. We could also do z of t is z naught plus r e to the negative 2 pi I t. T goes from 0 to 1. And the only difference now is because we have the minus sign, we start here, and then we go in the other direction, we would go clockwise. So those two should give us slightly different answers, because we're going about the circles in the opposite orientation. Fortunately, most of the integration we're going to do reduces to integrating along circles. And this is essentially the only parametrization we really need to learn. So the idea is you have some kind of curve like this, and you have a couple of points where it blows up, and it's fine everywhere else. And you want to integrate along this curve. What you do is you draw very small circles about each of these. And then as you're coming down like this. I come up here like this. I go around the circle, and I come back down like this. And then you take the limit as this gap goes to 0. And as this gap goes to 0, these two pieces cancel. And then you'll have an integral of this on the outside plus an integral of this. And you'll get it equals 0. Well, the integral of this is not going in the right way. This is going clockwise. We don't do things clockwise, except when we're trying to figure out when it's time to leave. We want counterclockwise. That's going to introduce a negative sign that will pull this over to the other side. So essentially, whenever I give you any strange region like this, we will always reduce it to something like this. So for those of you who did Green's theorem, can you raise your hand? Did you do stuff like this with the little slits and the slits getting thinner and thinner? A little bit, okay. That's the key idea. All right, so this is a good place to stop. It is always interesting to see that, in year N, I still do the same amount of material each day as year N minus 1, and we will continue on Friday.